Lesson 3, Kirchhoff's laws. There are two laws that you can use to solve any circuit. It is possible to do this algebraically, and in fact, the first couple of years that I taught Physics 12, I gave these as algebraic laws. Each time you ended up having to solve a system of equations where you had two variables and you either substituted one equation into the other one or you used the addition subtraction method. And it worked. And then I had a teacher show me the method I'm about to show you, with which Mitchell was much better. There are two laws. There's a current law. I'll abbreviate it as KCL, Kirchhoff's current law. And there's going to be a voltage law. I'll abbreviate that as KVL. Current law basically comes out of the fact that charge is conserved. You can't lose atoms. More specifically, even on a fundamental level, you lose electrons or protons. You know what? We're pretending it's the protons that move, even though it's not. You can't lose protons. The number of protons in the system is constant. It says that at a junction between wires, current flow splits or combines and continues to flow downhill. When the current splits or combines, no charge is lost, so the total flow into the junction equals the total flow out of the junction. Say, what? It's much easier to go here. How many round circly things are there here? Let's say right here I have 2 amps. And here I have 1 amp. I have 2 amps and 1 amp flowing into the same junction. I'm going to get 3 amps out. That's the current rule. As an equation, you can write it like this. The sum of all the current into an area has to equal the sum of all the current out of an area. We'll write that down. It's not on your formula sheet. We'll never actually use it that way algebraically. We'll just say skiers can't vanish, which is my ski hill analogy. If skiers vanish, you've done something horribly wrong, and you have to call it a search party. So it's much easier just to start solving stuff. It says, find the unknown currents. Okay. I always try and start right at the battery, the chairlift, and I label which way is downhill. That's also Kyle, my good old, hey, I've written something down, I feel better, routine. Okay? How many amps are leaving the chairlift? I don't know. How many amps right here? I don't know. How many amps right here? I don't know. How many amps right here? How many amps must be right here? 1.75 amps. How many amps must be right here? 1.75. You know how many amps are leaving the chairlift? I'll fill that in just because it's something I'm always interested in. This circuit has a total current of 1.75 amps. You're going to find, Alex, when you're solving a circuit, if you know total current, the question falls apart every time. Alex, how many amps right here? How many amps right here? How many amps are going through this resistor? 1.75 amps. How many amps are right here? How many amps go through this resistor? How many amps right here? How many amps right here? Yep. And you'll notice current is flowing downhill from the positive part of the battery, uphill, top of the chairlift, through the circuit to the negative part of the battery, to the ground. Let's add one with some splits. I always start at the battery, and I'm going to label downhill. Kevin, how many amps are leaving the battery? 3. And I love the fact you said, don't know, but 3. Hopefully you'll get good enough so you'll say, yeah, you know what? It's gotta be 3. I'll label that just for giggles, even though they didn't want me to. So ready, Kevin? How many amps right here?
3 amps.
How many amps went this way?
0.8.
How many amps must have gone this way? 2.2. The reason is there's a total of 3 amps in the circuit. That means I better not, because I heard somebody say 3.8. No. 0.8 and 2.2. We split up. Let's follow the right-hand fork, the right-hand circuit. So Kevin, how many amps right here?
2.2.
How many amps must have gone through this resistor then?
2.2.
How many amps right here?
2.2.
How many amps right here?
2.2.
Which way, flowing left or right?
Left.
I'll circle that. How many amps went through this resistor? And then when they recombine, how many amps right here? How many here? Which way? This is Kirchhoff's law for circuits. Current splits up and recombines. Charge is conserved. Skiers don't vanish unless you're going to get shut down. Right? If you're a ski hill and you're constantly having skiers not come back, they're not letting you stay open. All I can do is just make it more complicated. Okay, like this. Dale, do I know how many? Oh, first of all, now, this time with no arrows, a good habit to get into, Kohei, a good habit to get into, Kiowa, put your phone away for the rest of class, face down. Thank you. A good habit is to label downhill. In other words, before I start, I'm going to say downhill, downhill. This is downhill, that's downhill. This is downhill, that's downhill. That's downhill. Current goes this way, current. I know which way I'm going to be moving my eyes. Takes 1 second, but it's great bang for your buck. I always try and start at the chairlift. Do I know the total current, the number of skiers on the hill? Dale, how many amps went this way?
8.
How many amps went this way?
5.
Dale, how many amps were right there then?
13.
How many right there then?
13.
How many right there? Oh, how many right there then? I now have total current. I'm telling you, this question is going to fall apart. It's going to. Oh, and the rule of thumb, Travis, when you get to a really nasty question, where do I start? Try finding the total current, because if you can do that, the question's going to fall apart. So, Dale, how many amps went this way?
8.
How many amps went this way?
5.
Let's keep going, keep going, keep going. How many amps went this way?
2.
How many amps went this way?
3.
Gotta be. How many amps then went through this resistor?
3.
3. How many amps right here?
3.
Still 3. How many amps right here? And how many amps right here? 13. There's Kirchhoff's rule for currents. And you'll notice if you do it right, you can do it in your head. Even with yucky decimals, it's adding and subtracting. It's, not too bad. You all handled the 2.2 and the 0.8 pretty well. Ooh, cool. I think I need to make this one a teeny bit smaller. There. Ah, no. Label downhill. 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 I guess that's downhill, that's downhill, that's downhill. Downhill. That way is downhill, that way is downhill. That way is downhill, and we come back together. Is that okay, Clay?
Yeah.
Start here. How many amps?
5.
How'd you figure that out so quickly? They didn't tell me. Now, you're right. If you want my ski hill analogy, here's what we're saying. 5 amps start off together. Right here, they come to a 3-way fork in the path. We shake hands. 0.5 amps say they're going to go this way. 2 amps say they're going to go this way. 1 amp says, 1 amp. How do I know? You know what? I don't know that yet. But we meet up back here. Again, shake hands. Let's keep skiing together. So, Clay, you said all of the skiers have met back together. All of the current is sitting right there, and you went to here and said 5 amps. Good. Now that I know that, is that the total current in the circuit? Say yes. It's going to fall apart, because how many amps, you saw I did it accidentally without even thinking about it. How many amps must be here?
2.5.
Gotta be. Okay. Oh, and how many amps must be over here?
3.
Sorry? Gotta be. Okay. By the way, eventually we're not going to label the current on the actual wires. All we're going to start to label are the resistors and the battery. That's what we're interested in. Label downhill. Also, by labeling it downhill, you kind of move your eyes through the circuit and you get a feel for how it's put together. Vikas, do I know the total current leaving the battery?
4.5.
Okay, I'm just going to remember that this time. Now we're getting more advanced. We're getting a little more lazy. So how many amps right here?
4.5.
How many amps? Okay, how many amps right here? How many amps went this way?
1.
How many amps went this way?
3.5.
Must have been. Let's keep going down this ski run, down this branch. How many amps went through this resistor?
3.5.
How many amps went through the bottom here?
3.5.
How many amps went through this resistor?
1.
Gotta be. And there we get our 4.5 amps back. Ta-da. I can see why you're able to teach this to grade 9s, Mr. Dewick. Yeah, it's circuitry. That's the current law. We can even go a bit better than that. If you want some shortcuts, I'll be honest, Josh, you can survive perfectly fine without these shortcuts, but for what it's worth, the current, the amount of flow, the current along any path depends on the resistance of that path. Let me show you what I mean. If the resistance of each path leading away from the junction is the same, what can you say about the current? So if I have 6 amps and I have 2 identical resistors, how would it mathematically be nice and make sense for the current to split up? 3 and 3. What if one resistor was twice as big, half the current of the other one? What if one resistor was 3 times as big, 1/3 less current? Because as resistance goes up, current goes down. We said resistance was sort of like how deep the snow was, and if the snow gets really deep, you can't get as many skiers at a time because they have to go really slowly. So, 6 amps, small resistance versus big resistance. Which current will be bigger, I1 or I2? I'll draw, you know what? I'll do my usual trick of big letters meaning big, small letters meaning small. I1 will be much bigger than I2. In fact, we can even go further. Part C, I've never really bothered memorizing. I have used it once or twice as a shortcut. I don't think I've ever had to use it to solve anything. I was always able to find a different approach. If they're simple ratios of each other, we can relate the currents via the same ratios. In other words, if this is R and this is 2R, how will the current split up? Which current will be bigger, that one or that one? The one in the middle or the one on the right? Okay, the middle one will be bigger because smaller resistance, and it'll be in a 2-to-1 ratio. How can you break 6 amps up in a 2-to-1 ratio? I'll be honest, Mitchell, I have used that trick there one more time than never. I think I've used it once. And I'm willing to bet if I thought about it, I could have found a different way. The one I do use fairly often as a shortcut is, oh, the resistances are identical, the currents are identical. I'll take that. It splits in half. Voltage law. This one is a little more complicated. Kirchhoff's voltage law, KVL, basically comes out of the law of conservation of energy. It says this: as charges flow around a circuit, they experience voltage gains, batteries, and voltage losses, resistors. The gains and the losses have to cancel out. This is what it says. In my ski hill analogy, it says this: if you ski around any section of the mountain and you end up back where you started from, you must have started and ended at the same height. If you ended up back where you started from, you must have started and ended at the same voltage. Any height you gained, you must have lost to get back where you started from, or any height that you lost, you must have gained back if you've ended up at the same location on the mountain. Mathematically, we write it this way. the sum of all the voltage gains has to equal the sum of all the voltage losses. Okay, fine, I've done the algebraic version. Kiowa, I'm not going to use the algebraic version. I'm going to give you the ski hill intuitive version. So in terms of my ski hill analogy, Kirchhoff's voltage law says that the chairlift takes you to the top of the mountain, and if you get back down to the bottom of the mountain, you have to lose all the height that you gained. You can't reach the bottom of the chairlift without losing all of the height that you gained. In other words, if the chairlift lifts you 100 meters and you ski down 80 meters, I guarantee there's no way you're at the bottom of the chairlift. It's impossible. Okay? Or if you start out 40 meters high on the mountain and you go up a chairlift and you ski and you end up back where you started from, you have to be 40 meters high again. Voltage is height. Ready? It says find the unknown voltages and voltage drops. Let's do our usual, hey, that's downhill. Ready, Spence? How high is the chairlift? What's our voltage gain? How many volts high is this mountain? Those are all the same approach to the same question. How many volts do I have to lose when I get back down to here? 20. How many volts do I have right now?
20.
Have I gone down a ski run yet? So I'm still 20 volts high. How high am I here? Still. How many volts do I lose going through the first hill?
8.
How many volts high am I right here then?
12.
Has to be. Then I have don't know. Don't know. Wait. How high am I here?
0.
How high am I here?
0.
How high am I here?
0.
How high was I here?
12.
How high am I here?
0.
What must I have lost going through that resistor?
12.
Got it. That's the voltage law. If you want, it's typically phrased, if you do a closed loop and end up back where you started from, all the gains have to cancel out all the losses. And I used to teach it that way, and this is where we got systems and stuff. The ski hill analogy is much more intuitive. Let's go skiing. On a day like this and weather like this, Mr. Duick, I'd like to think I'm skiing. Okay. Ready, Trav? Okay. Let's label downhill. Downhill, 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 downhill. I'm going to ski in that direction. The current is flowing in that direction. How many volts high is this chairlift? Okay, so how many volts right here? So right here we come to a fork in the road. All your current, all your skiers are going to split up. They're going to shake hands. Some are going to go one way, some are going to go the other way. Let's go down this hill. Have we gone down a hill yet right here? Right here? So how many volts are we still right here? Still 10. Okay. With me so far? Whee! We go down this hill. I don't know how high this hill is, but follow me, follow me, follow me, follow me. How high am I right here? How high am I right here? How many volts am I right here? How many volts am I right here? How many volts must I have lost? There you go. So far, so good? Let's keep skiing. Let's go the other way. How high? How high still? Whee! How high? What did we lose going through the resistor? Now this bugs kids. Add up the two blue numbers. What do you get? Mr. Duick, how can a 10-volt battery give us 20 volts? No. Voltage doesn't work that way. What I'm telling you is a 10-volt battery can give you any pathway that's 10 volts high. And there are two pathways in this circuit. Each of them is 10 volts high. We would say that this circuit is set up in parallel, and we'll talk more about that next lesson. Yes?
Like, wouldn't the amps split?
Yep, the current splits, but not the voltage.
So, if you say 10 joules per 1
Hang on, 10 joules per coulomb. Okay, voltage, yeah.
So you get to a junction, then the coulomb split, so you only have 10 joules per 0.5 coulomb.
No, because the energy is split as well.
Oh.
Yeah, the energy, because each current, each charge would take its energy with it. Good thought. Nice try. I'll miss your thought-provoking questions, my friend. We only got a few more weeks of this. You're one of those, I always got to go back to first principles here. A few more weeks, what, 5 weeks? Right? 6 weeks and we're done.
Yay.
I think it's 13 classes. Mm-hmm.
Really?
13. Ready, Clay? Let's go skiing, you and I. Mummy, I went skiing today. Clay, let's label downhill first. Downhill. That way's downhill. That way's downhill. Again, I encourage you, do that. That 1 second or less really clears out a bunch of mistakes. How many volts is our battery, Clay?
12.
So we have to lose in any loop 12 volts. So you ready?
Yeah.
How many volts right here?
12.
Still 12? Now, apparently, everybody goes down this ski hill, losing,
8.
leaving,
4.
and then we're going to split up. Spencer's going this way, you and I are going this way. Whee! How many volts right here?
4.
How many volts right here?
0.
What do we lose?
4.
Hmm?
It's the same on the other side.
Oh, are you saying that if circuits are set up in parallel, you'll lose the same voltage going down each path? Hey, that would be a good handy little shortcut trick to notice as well. I never tell kids that. I'm glad you spotted it. So you're telling me it's going to be 4 volts, 0 volts, and we lose. And again, if you add up all the voltages on the resistors, you have 8 plus 4 plus 4, which is 16. That's not how voltage works. You don't add it up and say it has to cancel out the battery. If you add up any closed ski run, there's a closed ski run, I guarantee that'll add to 12 volts. Gain 12, lose 12. And here's a closed ski run, and I guarantee in that ski run, you'll gain 12, lose 12. That's how Kirchhoff's voltage law works. Jason, you want to go skiing? Let's go skiing! Let's label downhill. By the way, Jason, are you noticing our diagrams are getting kind of cluttered? Very shortly, we're going to say, let's just label resistors and batteries and not label all the wires. But for now, how many volts does this circuit supply? Okay. How many volts right here then? I agree. Everybody goes down this hill together. How many volts right here? How many volts right here? How many volts right here? Cool. Do you want to go down the middle run or the right-hand run? Right-hand run? How many volts? How many do I lose here? Leaving? How many do I lose here? Don't know. Leaving? Don't know. How many volts right here? Don't know. You know what? I think we should have gone down this run first. You ready? How many volts high? How many do I lose? Leaving. How many volts high? How many volts high? How many volts high here? What must I have lost here? Hey, let's go. Now let's go. And this, by the way, I'm glad you did that. If you run into a dead end, go the other ski run, Mitch. Like if you run into something, I don't know, 2 of these things, I'm telling you, you'll be able to figure it out from the other run. Hang on a sec, Clay. So J, 60, 50, 45, 45. We have 35. We lose 27. How many volts must we lose here? Well, I guess we have to be 27 volts at the bottom since we're meeting together. The only way that skiers can meet up again is they're at the same height, the same voltage. So how many volts must I lose going through the mystery little resistor there? 8. Clay, you had a question?
For the voltage, does it always have to be 0 when you go back in the battery?
No, but generally we'll define that as 0 to make the math nice. When wouldn't it be 0? Later on in about 4 lessons, we'll look at circuits with more than one battery.
And then, what if it's a positive, negative one? So the negative is the positive?
You
Are you
would-
familiar with this?
You talking about rechargeable?
No, I've worked on a few where I was just curious.
Where the negative is the positive.
Yeah. So
Well, you would just flip the current, I think.
that's
Hold,
what
hold
meant
that. I
by-
think I'm answering your question wrong. So later on, I'm going to be looking at complicated circuits, and what I will have are 2 batteries facing each other. I'll deal with that, okay? And we'll deal with rechargeable batteries, and we'll deal with circuits where you just have more than one battery. And but you'll find actually, it still works. I've just gotten good enough that now I can see how it all works. It's a nice system. So, useful conclusions to draw from Kirchhoff. Oh, yes.
If you go up, and on the second path, on the right one, you don't have the second resistor.
Here? 10 volts.
The second one, if you don't have that one.
Oh, if I don't have that one? Then this would be a poor, well, first of all, if this wasn't here, and this is 15, and this is 27, then this resistor here would end up being an 18 volt drop. It would be having more voltage than it was designed for. So you might end up frying out the circuit.
And how does the second know?
Just the current, the voltage rules have to work that way. It's impossible for the charges to get through here without losing all of their energy. The same way, how do I know to get down to the ground? Gravity. Well, there's the current flow. It takes care of itself. It does. Hold the thought, and when we get less numbers, I think it'll become clearer.
This one's
2 useful conclusions. For any complete loop, the drops equal the gains. And no matter which way you go between 2 points, the drops must be the same. In other words, if you split up and meet up, the voltage drop this way adds to 18 volts. The voltage drop that way is also adding to 18 volts. I think Clay spotted that. It's a nice little shortcut. I've debated that. In fact, I've debated deleting this from the notes. I wrote here, well, my friend wrote here, to see voltage relationships, it's sometimes helpful at first to redraw the circuit so that all resistors are pointing downhill. For example, consider the previous circuit 5A, this one. You could redraw it like big chairlift. Everyone goes down the first hill right there. And then some people go left, some people go right. They split up and meet up. I honestly find this easier. I know some kids find this, but you know, I'm lazy. I don't like redrawing things. Okay? 5B, this one, could be redrawn as big chairlift. Everyone goes through one hill, and then some people go through 2 small bunny hills. These people go through one big hill. They shake hands, they meet up, and they all go down the final hill together. I'm not going to bother redrawing. There will be some that are so tough that we have to redraw them, but we'll be redrawing them much simpler. We'll be rewriting them as their simplest mathematical equivalent, which usually means 1 resistor and 1 battery. I'm lazy. Example 6 says write equations rating the voltage drops. I'm going to say put. Let's go to example 7. If there are several resistors in the same path, this is partly going to answer your question here. The charges will lose a fraction of their voltage in each. And this actually comes out of the current rule. So these 2 resistors are identical. What can you tell me about the current in each of these? How do the current compare to each other? Are there any junctions? Are there any ways for things to split up and meet up? So what can you tell me about the current here compared to the current here? If they both have the same I and they both have the same R, what can you tell me about their V? More specific, since my chairlift is 30 volts and each voltage has to be identical, how many volts do I lose in each one? Quick look at money. How many volts do I lose in each one? Come on, people. 15 and 15. Yeah. Again, as I mentioned before, this is a nice shortcut, Trav. I've never really bothered memorizing that, oh, if I have identical resistors and I have identical currents, the voltage is good. I usually just crunch it quickly. But, okay. Oh. If the resistances are not the same, now, both of these still have the same current because they're hooked up to the same wire. They have to. That's the current law. If I have the same current times a big R versus the same current times a small r, which of these will have a bigger voltage? Why? I times big R will be greater than I times little r. Here's V1, here's V2. And this is why I was saying it just all takes care of itself quite nicely mathematically because of the Kirchhoff's laws. It really does. Oh yeah, and again, if they're simple ratios of each other, we can relate the voltage drops via the same ratios. So, same current. Yes, because same wire. Big resistance means bigger voltage. You know what? Twice as big a resistance means twice as big a voltage. How can I split 30 volts up into a 2-to-1 ratio? I've used that one less time than never. I've never used it. But, okay, it's kind of cool. Instead, here's what we do. Now we're going to get into solving circuits. Although it's helpful at first to label voltages everywhere, we're going to stop doing that. From now on, we're going to label the battery, we're going to label the resistors. Everything else, I say, poof. So, example 8, I like this question, I like this except these are too easy. But you're going to have a bunch of circuits to solve on your test. Here we go. It says, find the unknown voltages, currents, and resistances. You know what? And powers. What are we going to use for equations? Over here in the margin, you can write V equals I times R, and power equals V times I. Manny, you going to make it? Because you're low and looking pretty low. Okay. Because I'm coming to you, Manny. Label downhill, 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 downhill. Manny, do I know how many amps are in this circuit? How many amps are leaving the battery? Yes. Is that the total current? Say yes. This question's going to fall apart. Okay. By the way, what's the resistance of this resistor in ohms? If you know 2, you know all 4 things. Do I know 2 things? Yep. So use V equals I times R, get the R by itself. Come on, people. What's the resistance in ohms? Man, do you have a calculator here? Get it out. How am I calculating? What am I typing into my calculator? Huh? Okay, 6 divided by 4. What is it? So this is 1.5 ohms. If this was a light bulb, how many watts is it? $24 watts, yes? V times I. Let's keep going. Ready, Manny? How many amps went this way? How many amps went this way? We filled in all the currents. I always do that first. Step 2, we go skiing. How high? How many volts do I lose going through this hill? Leaving? I don't know how high this hill is, but did it get me down to the ground? How high must this hill have been? Hey, I know 2 things now. I know 3 amps and 12 volts. I can tell you the resistance, and I can tell you the power. If I know 2 things, I know 4 things. In fact, I can do the resistance in my head. Is it going to be 4? 12 divided by 3? It's a 4 ohm resistor. I can even do the power in my head. If this was a light bulb, how many watts is this light bulb? 36. You okay with how we got that? Right? V times I and V equals I times R. Let's keep skiing. Let's do the other run. So now, Manny, we're going to do this run, the outside run. Okay? How high? How losing 6, leaving. Don't know how high. Oh, did that get me down to the ground? Oh. How many volts do we lose in this resistor? Do I know 2 things? I know 4 things. $12 ohms, yes? And what's the power here? So let me give you, I told you this was really too easy, and it is. Here would be a nice question. Instead of me saying solve the circuit, if I gave you this circuit and I said to you, this circuit contains 3 light bulbs, which one's brighter? Which one is brighter? My mom says I'm not the brightest bulb. No, she means something different. Which bulb's brighter? The middle one, yeah. Which, if you didn't know how to do this, would be terrifying. What? There's, no. Find the power. And in anywhere in the circuit, if you know 2 things, you know 4 things. 36 watts is brighter than 24 watts, is brighter than 12 watts, is brighter than most of you. Never mind. Okay? Let's do some more. Mr. Do-It, this is almost fun on a hot day. We get to go skiing. I know. Vikas is stretching. Vikas, good. Glad to see you're stretching. You're loosened up. That means you've stretched out. Likely no injuries. We're going to go skiing. So B, labeled downhill. So downhill is going to be this way, this way, this way, this way, this way, this way. Yeah? First thing I start with, I always want to try and find total current. Did it tell me how many amps right here? It should be nice. Did it tell me how many amps right? Because that would be total current. How many amps here? How many amps here? How many amps here? How many amps leaving the chairlift? I know total current. You know what? This question's going to fall apart. By the way, what's the resistance of that particular resistor? Need your calculator for it. You guys okay with how we're finding the resistance? It's going to be V over R, right? Sorry? 8.4, is that right? 8.4 what? Ohm. By the way, throw the units on because you might forget what number is what later on. Oh, we can also, if this is a light bulb, tell you how many watts the bulb is, or if it's an electronic device, how much power. Sorry? 21 watts? I don't think so. It's got to be 21 times 2.5, right? It's V times I. It's got to be 21 times 2.5. It's going to be 42 plus 10.5. It's going to be 53.5? 52.5, that's what I said. Power is measured in watt? Okay. Then I go look if there's any part of the circuit that has 2 things on it. Only one piece of information, only one piece of information. Because if I know 2 things, I know 4 things. Now I ski. You ready? How high?
35.
What do we lose going through here?
21.
Leaving.
Uh,
Use your calculator if you need to, but get it.
14.
Okay. Do you want to go down the middle or the right?
Down the middle.
How high? Don't know. Oh, did that get me down to the ground? I now know how high that one is. How high?
So 14.
I know 2 things. I know 3 things. I know 4 things. Right? As soon as I know any 2 of power, voltage, current, and resistance, I can find everything else. Resistance I can do in my head. 14 ohms, yes?
Yep.
Power I can also do in my head. 14 watts, yes? It's a nice part of having 1 amp. I know my 1 times table. How many volts in the right-hand resistor?
35 as well.
How high?
35.
What do we lose?
8.4. Sorry, 21.
Leaving.
14.
So if we lost 35, we would now be at negative, do you see it?
Yeah.
By the way, also, look up. Here, you and I are skiing together. We split up. We shook hands, and then we met up here. If you lost 14 volts going down here, I must have lost 14 volts. Otherwise, how the heck could we meet up afterwards? Be at the same height, same voltage. So 14. What's the resistance? What's the power? $14 divided by 1.5, which is what?
9.3.
9.33333?
Yep.
9.3 is good enough. Power, 14 times 1.5. 21?
Yep.
What's the brightest bulb in this circuit? Left, middle, or right? Left, 52.5. Okay. Or, if this was an appliance, which of these 3 appliances is going to get the hottest? The left one. It's moving the most heat around. Okay. Couple more done. Having fun, Mitch? Yeah? Raj, let's go skiing. It's labeled downhill. Downhill, 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 downhill. Raj, did they tell me total current in this question? No. Can I figure out total current? Yeah. It's going to be at least 1 amp. I can tell you it's more than 1. Raj, any thoughts? I saw you reach for your calculator. Figure what out? Can you tell me what you're trying to do? In the first one? How are you figuring out the amps in the first one? Oh, okay. What? Oh, how many volts must I lose in the first one? Is that what you said? How many volts? Got to be 5, right? 40, don't know. 35, ground. That's a start. What else? I wouldn't assume. What, huh? Oh, because we can shake, this is what Clay spotted. Because we can shake hands and meet up, if I lose 35 going through here, you're telling me I'm going to lose 35 going through there? Now, why is that so nice? Because now I know 2 things. I know 4 things. I can tell you the current must be 7 amps, yes? V over R. I can tell you the power here must be 7 times 35, 210, subtract the 3, 245 watts? This is an appliance, probably like a blender or something like that. Oh, I can tell you the resistance here, 35 ohms. They didn't ask for it, but I can tell you how many watts this appliance is. I can do that in my head. 35 times 1, 35 watts. Can I fill in how many amps are right here? How many? 8. That's the total current. And Dustin, now that I know 2 things, I know 3 I know 4 things. Resistance is going to be 8 divided by 5, 1.4? No, 1.8? 1.6. Yeah, 1.6. It's 5 divided by 8, Mr. Dewick. So it's going to be, let's see if I can recover, 0.625? Whew. Don't do that, Mr. Dewick. Oh, and how many watts is this little appliance? 40. You know what? That could be a light bulb, a 40-watt bulb. Definitely, this is probably not a light bulb. I mean, they do make bulbs this bright, like for heat lamps, like for, raising chickens in barns and things like that. Or the heat lamps you see in restaurants where they're having the food sitting under. But it's a lot of heat. Nick, would you come skiing with me? Let's go skiing. D. First thing I always look for is labeled downhill. Downhill, 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 downhill. Nick, did they tell me how many amps are leaving the battery? How many skiers are leaving the chairlift? What? Oh, this question's going to fall apart. You're right. Total current right here is 5 amps. I'm telling you, if I know total current, this question's going to fall apart. Do I know, Nick, 2 things on this resistor? Say no.
No.
Let's keep going. Oh, do I know 2 things on this resistor? Then I know all 4 things. What's the current here? Have to be. You guys okay? I have no idea if you guys are like, how do I find? It's V equals I times R. So I equals V over R, yeah? 15 divided by 5, yes? How many amps?
3.
How many amps over on the other wing, on the other path? 3? 2? Right? How many amps down at the bottom here, Nick? Thank you, Nick. Hey, Nick. I just wrote down 2 things. That must mean I know 3 things and 4 things. I can find the voltage. V equals I times R. I can do that in my head. 20 volts. I can tell you power, 100 watts. V times I. Let's ski. You ready, Nick? How many volts? How many volts do I lose here? Don't know. How many volts do I lose here? How many volts do I lose here? Yes? Does that get me down to the bottom? So if I start 70, don't know, lose 15, lose 20. How many volts must I lose there if that got me down to the bottom? Could you use your calculator and not give me and actually give me a firm, confident answer? What are you doing mathematically? Tell me.
Subtracting
More specific with numbers.
70 minus 15.
Absolutely. 70 minus 15 minus 20, which I'm pretty sure is 35, but double check me. Is it? Hey, you know what, Nick? Now that I know 2 things, I know 3 things, I know 4 things. Resistance is going to be V over I. The resistance is going to be 7 ohms. And I can tell you the power is going to be V times I. It's going to be 35 times 5, which is 150, 175? Watts. Oh, what's the power of this resistor in the middle here? 45 watts. V times I. Okay. What haven't we filled in yet, Nick, my friend? Right-hand side. Any thoughts? Gotta be. Which means the resistance is 7.5 ohms. And it means what? It means, power is 30 watts. Anything you need me to find, I can find. There is a typo here. I don't know why, and I can't fix it. This line right here should really be right there with the battery. And if I go draw, color, white. So pretend yours looks like that. I think I've told you these notes were originally typed by my friend in Word 95 for Mac. So they're slowly starting to degrade. Question, Kiowa? I'm deciding. I decided the circuit's going down. Do you want me to put it on the top? I've drawn it there now, so downhill is downhill. And I kind of did that on purpose because a lot of the circuits so far downhill has been uphill. I thought, let's go downhill from the battery. Okay? Downhill is boom, 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 boom. Alex, did they tell me total current in this anywhere? Yeah, where? Did they tell me total current in amps in this anywhere? No. Yeah. Did they tell me, next thing I look for, is there any resistor where they told me two things of information? Let's go target that. This resistor right here, what else can I find there? How? In your head. 8 divided by 2. Don't lowball me on this, my friend. Yes? It's a vibrating phone. I'll live with that. How many amps? Ding, 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 ding. You just found total current. Isn't that? Question's going to fall apart. So you ready? How many amps? How many amps? Don't know, because I don't know the split. Is there any other resistors where they told me two things? Then let's ski. How high? What do we lose? Leaving. Let's go this way. How many volts must I lose in that middle hill? Yep, because that got me down to 0, right? You know what that means? I know 2 things. That means I know 3 things. I know 4 things. How many amps must I have in that middle resistor? It's going to be V over R. In your head, 24 divided by 10. It's dividing by 10. Yeah, 2.4. How many amps? How many amps? How many amps went this way? In your head, how many amps went this way? Oh, thank you. I was worried. Oh, 1.6 amps. How many amps in this upper resistor? Nope. How many amps in this upper resistor here? Still 1.6, because there was nowhere for them to go. But why is that so nice? Because, Trav, in that upper resistor, I know 2 things. You know what that means. I know 4 things. So what's the resistance here? It's going to be, this one I'll let you use a calculator for, 10 divided by 1.6. 6.25. Well, All I need is this. Let's go skiing again. Ready, Alex? Way. If you ski that way, you should be able to figure out how many volts that bottom right resistor has to be. Let's see. We start with 32, right?
Yeah.
How many do we lose here? Don't know. How many do we lose here? So I lose 8. I lose 10. I start with 32. What must I lose there for the math to work? I think it's going to be 32 take away 18. Right? Yes? Good. Go. Do it. Head or calc, I don't care, but let's get her done. What?
14.
So you're telling me that this is he right?
Yeah.
Do we now know 2 things? We know 3 things. Or 4 things. I haven't bothered finding the power, but it's going to be V times I, V times I, V times I. Resistance is going to be 14 divided by 1.6. 8.75 ohms. Well done. That is closer to the level of difficulty I'll expect. No, that there is a C+. That's a C+. I wrote here, light bulb questions are good tests of student understanding of Kirchhoff's laws. Brightness is related to power. So a nice way, instead of me saying, Amelia, solve the circuit, I might say, prove which bulb is brighter. Really what I'm saying is find the power from each bulb, and to do that, you're probably going to have to find the voltage and the current and the resistance. Just saying. Example 9. These 2 bulbs have the same R, the same resistance. Which one's brighter? Let's see if we can prove it. How many volts? How many volts? Has to be. How many volts in B? So I'm going to make a little note here. Yes? Question says same R. Yes? What can you tell me about their currents if they have the same voltage and if they have the same resistance? Just give me 1 second here. Hang on, just please give me 1 second here. Sorry. Hey, if you have the same V and you have the same R, what can you tell me about your current? So I'll put a little therefore. And if you have the same current and the same voltage, what can you tell me about your power? What can you tell me about the brightness? Therefore, same power, same brightness. What was that, Clay?
B is going to be dimmer than
Let's see. Bulbs are identical. So if they're identical, I know same R. Yes? What can you tell me about the current going through them? Oh. Same I? Yes? So what can you tell me about their voltage if they have the same I and same R? In fact, I can even be more specific, 5 volts and 5 volt, but same voltage. If they have the same voltage and the same current, what can you tell me about their power? What can you tell me about their brightness? Have I convinced you? So your initial guess was wrong, but we've reasoned our way to the correct, yes? Therefore, same P, same brightness. You need to practice this. I'm going to be giving you a lot of homework because you need to practice this. This is the fundamentals. You're going to Playland tomorrow. Shut up. Number 1, 2, 3, 4, 5. I might. We'll see.
You went all the way from 1 to 3.
I'll skip 6, 7.
You were wrong.
8, 9.
He's not gonna do 13. He's not gonna do 13.
10.
He's gonna smile.
The smirk going instead of doing
I skipped 11. 12 is good.
Yeah. Oh, there's a no.
You're also going to be getting homework at Playland, but if you hustle, you can get all your work done at the ride assignment completed at Playland. But every year, there seems to be 1 or 2 people that have a weak link in their group chain. We finished it all, but so-and-so hasn't done their ride. Well, you better bully each other into getting the rides done.